So let's continue with our lecture. I think this will be lecture 4, I think, or maybe lecture 5, because the previous lecture was recording for almost 2 hours. I will try to split the video, so this will be probably lecture 4 or 5, I'm not sure. So the previous lecture I showed we encountered some problem, especially so what we did is let me quickly go through. So what we did in the previous lecture is we took the ethylene dichloride from the oxychlorination and ethylene dichloride from the direct chlorination reactions. We combined them using a mixture. So we mixed both of the streams, and we took some product stream. This product stream will be at 60 degrees and 4 atmosphere, or 4 kilopascal, which is very low for some reason. Okay, here there is a problem. So 4053, and the outside temperature is 4 kilopascals, and this one is 1.5 atmosphere or 150 kilopascal, and the exit stream we have 4 kilopascal and 60 degree centigrade. So and then we used a cooler to cool the temperature back to 15 degrees centigrade. Let's put it to 4 atmosphere. 4 atmosphere. And then we connect it to a flash column to separate, to purify. Okay, before the temperature was at 4 atmosphere. That was the problem, I think. Not 4 atmosphere, 4 kilopascal. So I changed the pressure back to 4 atmosphere. That should be equal to 405.3 kilopascal. So the pressure, that was the issue. So I fixed the pressure term here. So what we are going to do is we are going to maintain the temperature at 15 degrees centigrade and 4 kilopascals. 4 atmospheres. That's roughly equal to 405 kilopascals. So at this pressure and temperature, what we are going to remove is we're just going to remove or separate the light materials. In this case, it will be ethylene. As I said in the previous lecture, they are just hydrocarbons, so they can easily come in the top, and then we will get the much purer ethylene dichloride in the bottom. Yeah? So if you click to the stream 10, if you check here, if you go to composition, in the vapor phase we have some oxygen product, air products. So this one will come out in the gas side at 15 degrees centigrade and 4 atmospheres. So because the pressure is above the atmospheric pressure, so it will come in the top. The air product should come outside the flash separator. And at 15 degrees centigrade, water will be much lower than the boiling point, so it will be in the liquid format. So ethylene dichloride and some of the water will come out here. Yeah. So only the lighter components will go in the top as gases. So this is good thing. So this one will purify our product, which contains ethylene dichloride, and our main objective is to purify the ethylene dichloride near to, and the target is around maybe we can even target for a 99.5% of purity. So let's do that one by one. So before that, what I'm going to do is I will bit organize this. So let's right click on the stream 10 and then just click show table. So we will keep an eye on the purity, and then double click on the table, click add variables, and in the physical type let's check mole fraction and click the master component. So we are worried about the purity of the ethylene dichloride. So what we do, so we click the ethylene dichloride here, add, and then press done, And then you can close this window. So what we see here is 35% of ethylene dichloride. So the remaining must be impurities. This is a bit funny, like it's very low, very low. If you click on PFR, plug flow reactor, ethylene dichloride composition, ethylene dichloride is here, contains 68%. I'm not sure, probably increasing the residence time will make any big difference. Let's try that. Let's adjust the residence time. Let's slightly improve the value. Before that, ethylene dichloride, press show table, double click on this table, and then press add variable, select mole fraction, master component, click ethylene dichloride, press done, and then close. So it's only 22% is ethylene dichloride. So let's try to increase the residence time. Let's see whether it makes any changes. So let's put 0.15 and then press reset. So before we had roughly 22%, so there is no big difference. So press continue. Yes. I don't see any changes happening here. So no big difference. So let's put it back to the original value, 0.09. I thought increasing the pyrolysis, the time may increase the conversion, and then you may change the I thought the mole fraction of ethylene dichloride in the product stream will improve. Nothing is happening, so let's keep it to the original value. So let's try to purify this. So in the stream 10 we have a 35% mole fraction of ethylene dichloride. We need to reach 0.995. That should give 99.5% pure ethylene dichloride. So let's do that. So as I said in the previous lecture, so we are adding a flash column. So this is to reduce the workload in the next unit operations, which we are going to use to separate or purify ethylene dichloride. Yeah? So let's check. We added a flash column, and this flash column is maintained at a temperature of 15 degrees centigrade and pressure of 4 kilopascal, 4 atmosphere. So, and let's check the stream 11 how pure it is. So just right click, show table. You get some table for stream 11. Double click on the table, press add variable, click here mole fraction, go to master components, and then select ethylene dichloride. Yeah. Press done. So we get near to 65% purity now. So this is not bad. So our goal is to reach 99.5% purity. So what we will do, so in the industries they use some water as extractor in order to remove the other unwanted undesirable products, something like so they use water as extractor to extract all the other impurities, so that at the end you will get only ethylene dichloride, a more purified product. So let's try that. So what we do is let's add an liquid extractor. So we have to search for that. Separator. If you click separator, you can see something. 3-phase separator, tank, component splitter, distillation column, absorber, reflux absorber, shortcut column. You see here liquid extractor. Click that and then drop it next to 0.11. Sorry, the stream 11. So this is a major unit operation, yeah, for your information. So just double click on the liquid extractor. So our inlet is obviously 11, and then let's call the top stream as so we will, okay, let's see, let's call top stream as 12, bottom heavy liquid as 13. So here we will use water as a extracting solvent. So this is not correct. Top stage shouldn't be 11. So we are going to supply stream 11 from the bottom. So it should be, there is something is not correct here. Let's close this. Let's delete. No, this is something, I couldn't click, the computer is not working well. So this should be stream 11. Now I'm going to delete the liquid extractor. Computer is not allowing to do what I want to do. So let's add the liquid extractor. Liquid extractor. So we are going to use water as extractor. So what we will do, we add a stream here and double click on that. Let's call it as water extractor, and then composition is just water. So we are going to use water as extractor. So it's going to extract all the impurities from the stream 11. So the remaining should be 0. And then go to conditions. So close this. Let's check the flow rate is around 1043. So we will put slightly above this value. Let's put let's put 1100 kilomole per hour. Yeah. It's not important really. We can check that. We can even change the value later. So let's go to conditions. Let's put a molar flow rate for a beginning, say 650 kilomoles per hour, which is roughly half of the flow rate of the stream 11. Pressure, let's maintain at the same 4 kilopascals, sorry, 4 atmosphere, sorry. And then let's maintain the temperature equal to column temperature 50. This is okay. So if you want, we can even start with a water stream from 25 degrees centigrade, 1.5 atmosphere, and then we can add a pump and heater to raise the temperature and so on. Okay, so this is not a big deal. So water extractor. So this is like a normal river water temperature, yeah. So around 15 degrees. So just to double click on, now we double click on the liquid extractor. So the inlet should be the extractor which you are going to use. So it should be a water stream, and then the stream that we want to purify is here 11. So let's assume that we are going to perform 5 different stages. So we are going to perform liquid extraction, like 1 stage, 2 stage, 3 stage, 4 and 5 different stages. Okay. So the number of stages should increase the purity. So based on the information from the industries, so roughly 5 stages are more than enough to achieve a purified product. Anyway, we can check that whether increasing the number of stages is increasing the purity of the material or not. So let's do that. So let's put the number of stages is 5. So let's call this overhead optional inlet stream. I think this is not correct. delete it. Bottom should be the stream 11. So we supply the stream that we need to purify in the bottom, and then the extractor in the top. So something like a counter current operation. And then top liquid, let's say 12. Bottom, let's call 13. To me, this looks fine. Material stream 12 cannot be attached here. Okay, I think I used the material stream 12 somewhere. I don't know. Maybe let's put 13. And then, oh sorry, 12 in the top, 13 in the bottom. Stream cannot be attached here. There is some problem. So let's put 14. Let's put next. So top stage pressure, let's maintain the same 4 atmosphere. And the bottom, let's maintain the same 4 atmosphere. Press next. Temperature, let's maintain the same temperature throughout the column. 15 degrees centigrade, 15 degrees centigrade. Let's press done. So everything looks fine. Press run. It's converged, so everything looks fine for the moment. Whether let's check whether it's correct or not. So let's delete this stream 12. It's not necessary. So your extractor water, it should come down. So this stream should contain all the impurities, and the top one should be the pure one. So remember, both are liquid. This is liquid extraction. So don't think this is something like a gas product just because it's on the top. This is a liquid extractor, so both should be liquid. So just right click on the top and then click show table. So we get some, and then double click on that table. Now let's check how pure the stream 14 is. Like let's check the ethylene dichloride purity. Add variable. I'm going a bit slow because it's better to learn this topic bit step by step. And it's okay to go slow, if not you will get confused. Because this is the first time you are going to use Aspen HYSYS, so it's better to go a bit slow. Let me check whether Panato is recording the video or not. I think it's recording. Press done. Okay. Close this part. So we get near to 92% purity, so this is not a bad thing. No? So if you see here, stream 10, the purity is around 35% ethylene dichloride purity. And then in the stream 11, the purity is 65%. And then after liquid extraction, we reach the purity of 92%. Yeah? So we can double click, just to play with the number of stage. I think it's not necessary, but this is only to show you how it works. So number 8, now we are running 8 different stages. So press run. And see whether the purity is improving or not. It says unconverged. Run it. I think I messed it up, or maybe my computer is slow. I'm not sure what's happening. I'm not sure whether my computer is running or something, or sometimes it will look like unconverged, but something will happen in the backside. I close this, and then if you're not sure what's happening in the background, you can press in the top something like on hold one time and then press active again. So it will run the simulations again. So something is not Fine, I think clearly I messed it up. So what I'm going to do is to delete this liquid extractor. Let me do it again. So we should have some patience, huh? And it's okay to give a try and see what will happen, because that's how we are going to learn anyway. Yeah? So liquid extractor. So bottom stage should be our stream 11. Number of stages is 5. Okay, this time let's put 8. Huh? Why not? And top stage inlet is water extractor. And then let's put the number 12 and 13. Press next. Pressure is 4 atmosphere. 4 atmosphere. Press next. Put the temperature to 15, sorry. 15 degrees centigrade. 15 degrees centigrade. Press done. Press run. Converged. Close it. So let's check the purity now of the stream 11. So just right click on the stream 11, show table. And once you get the table, just double click on the table. Press add variable. And then select mole fraction. Select master component. List the different components. Ethylene dichloride. Done. So we get 92%. So it doesn't make a big difference, 5 or 6. At the end of the day, the purity is 92%. Yeah? So the number of stage doesn't play a big role. So obviously you can play with a single stage, 2 stage, 3 stage, 4 stage, 5 stage liquid extraction, and then you can see the level of purity here. Maybe I can try to make a case study. This is something that we can do it in the Aspen HYSYS. Let me try that. Let's click case study. So if you click here case studies in the top, you will get this window. You can press add case study, find a variable. So let's click water extractor. What's the name of the unit operation? T100, okay. Find variable T1100. This is our extractor. And then let's change the number of stages. I couldn't find this for some reason here. Maybe we have to do it manually, I think. We have to do 1, 2, 3, 4, and okay. Let's close this one. Let's go. Let's stop this. We don't have to do anything at the moment. So just to look at the purity level, we are improving bit by bit. So that's the product stream. So we started from 35% purity, and then we improved it to 65% purity, and now our ethylene dichloride is 92% pure. So we need to purify it further in order to reach our goal, which is 99.5% of purity. If not, we will end up with some coking and also some scaling in the pyrolysis chamber with all the other impurities. So let's try to purify. So what we are going to do, we are going to use a reboiled absorber, and then we will try to purify it using the reboiled absorber. So let's add it. Click the separator, and then check for reboiled absorber. 3-phase column, blank column. Reboiled absorber is here, so it will have a reboiler in the bottom. So let's click it here. So double click on the Reboiled Absorber. So top stage inlet, that should be our product stream, which is 12. And then let's assume, let's do for 20 stages for a beginning. And then let's call the top product as let's put the number 14, and then bottom liquid as 15. And then for the reboiler, we need some energy to boil the liquid in the bottom. So let's put QE 6. This should be fine. Press next. Next. So top stage pressure, so let's keep it at let's maintain everything at the same temperature, so, and the same pressure. So throughout the column, 15 degrees centigrade, 4 atmosphere. So 4 atmosphere, sorry, it should be 4 atmosphere. Atmosphere. Pay attention to the units. And then reboiler pressure, let's put 4 atmosphere. Press next. Temperature 15. So press next. Press done. So press run the value. There is some problem with I'm not sure whether it's recording or not. It says some, let's check Panopto. I don't know whether it's recording. I think it's recording. So let's check. There is some problem with so it's not converged. I don't know what's the problem. Everything looks fine to me. You have some product stream. Oh, I think I did a mistake. Okay, there is a, this stream is connected. Oh my god. Okay, I know what's the problem. Let's delete it. Okay, yeah. I have to, the energy stream should be some new name. Probably I used the QE6 already. So let's click the Reboiled Absorber again. Let's add stream 12. Stream 12, and we already have 13 and 14. Let's put 14. And then bottom is 15. Let's put QE something like a reboiler. Press next, press next. So top stage pressure should be 4 atmospheres. And then bottom reboiler pressure should be 4 atmosphere. Press next. Temperature, let's maintain, we are maintaining the same temperature throughout the column, so it's at 15 degrees centigrade. So both should be at 15 degrees centigrade. Press next. Press done. Okay, now it should work fine, I think. So what is this? Flow basis is molar, and then specific value. Okay, this is something we have to think a bit. let's continue with the previous lecture. So what I did in the last lecture was I added the reboiler absorber with a main goal is to purify the ethylene dichloride. Let me recollect what I did. So we started from stream 11. So, and we can see the ethylene dichloride purity is around 65%. And then we added a liquid extraction column. So, and then we reached the purity of roughly 92%. And then I added a reboiler absorber in order to achieve the purity near to 99.5% or even more. Yeah? So let's do that. So I will delete the reboiler unit now, and then I will show you again how to do it. So it's very simple, but there are few things that you have to remember. Yeah. So if you want, you can think it like a rule or a set of procedure. So let's click the add the reboiler absorber, and then or absorber with the reboiler. In Aspen HYSYS they call the reboiled absorber. So let's the top inlet stage, this should be our feed 12. So this one, stream 12, sorry. And then our top, let's call 12, 13. Let's put some number 14. And then for bottoms liquid, let's call some number 15. I think this is okay. And then let's leave it to 10 stages. We can obviously increase to 12, 13, 14 or something. So let's leave it to number of stages is equal to 10. It's a default number. Press next, press next. If you don't know the number of stages, you can also check in the literature. There should be some information available. So, and then you can use that particular value here. So next. So I'm going to assume the pressure and the temperature in the throughout the column is same. So we know the pressure and temperature of stream 12 is 4 kilopascal and 15 degrees centigrade. So let's make this, let's add the same value. So pressure, I'm going to add 4 atmospheres. 4 atmosphere. Pay attention to the unit. And then the reboiled absorber, sorry, the reboiler pressure, sorry. Again 4 atmosphere. So press next. So as I said, let's assume the same temperature throughout the column, 15 in the top and 15 in the, so this is only an optional, but still I'm going to add 15 degrees centigrade. Press next, press done, that's it. And then now we can go to monitor. You see here this is still unconverged, and that's because we have to mention some more value here. So overhead production rate, so I'm going to give some number. Let's start, I'm going to give 700 for, so why this value? I'm going to give some number which is less than the feed flow rate. So just then press run. It's still solving. I always have problem with this absorber. Let's see what's happening. Not converged. Okay, let's put 200. Okay, it says it's converged. So this is a very low value when you compare to the feed flow rate. The feed flow rate is around here. You can see 742 kilomoles per hour. Follow the cursor. Okay, I need to pause recording the video. So this 200 kilomoles per hour, this is much lower than the feed flow rate, which is 742 kilomoles per hour, and practically we don't have this value 200 kilomoles per hour, so we just tried some random number which should be less than the total molar flow rate which enters the absorption column. So we started with 700 and the simulation was not converged, and then I entered the value 200, so everything looks fine for the moment. So what we are going to do is, let's keep this window here and now click on the stream 15. So this is where we are going to collect our product, ethylene dichloride. So what I'm going to do is just show the table and see how pure the ethylene dichloride is. So just double click on the table, add variable, and then check a molar, where is this, mole fraction, and then check the list of components, master component, mole fractions. So let's select ethylene dichloride and then press done. So what we have here is the mass composition is 0.99, so 99.8% of purity. So we can even reduce this number here. So it's almost 0.99% purity. We can change the number. So obviously it's low. So let's put back to 150. So we get almost a 99.1% purity. We can slightly improve the purity to 99.5. 200. Okay, 200 is a good value. So let's keep it to this number. So if you want, you can use it like a rule of thumb or some procedure to add absorption column to your process flow diagram. Yeah, so this is one way to design the design the absorption column using Aspen HYSYS. Yeah, I hope you all follow until this point, and also let's close. Maybe we can try one more value, 175. Okay, slightly increased flow rate and slightly higher than the desired level of purity. So it's 99.6% pure. So I'm happy with this number. So I'm going to close it, and then I will double click on 15, and then I will change the stream name to say pure EDC. So I'm happy with this. So what we are going to do is the next step. So the next step is to take this 99.6% pure ethylene dichloride, and then we are going to pyrolyze and in order to produce or manufacture vinyl chloride monomer. So let's do that, and also pay attention. So what's the temperature and pressure now? So the temperature now is 137 degrees centigrade, and the pressure is 4 atmospheres. So what we need to do now is okay, let's check the pyrolysis temperature. I don't remember exactly. So if you listen to lecture 2, I already mentioned what are the conditions for the pyrolysis and so on. So let's go back to our PowerPoint. Not this one. So if you come to our PowerPoint, I already added few things. So let's do this at 773 Kelvin, and this should give 60% conversion. And let's fix the pressure to 20 atmosphere, and then the residence time should be around 0.35 seconds. Obviously this is a very low number, and that's okay. If not, if you give extra time or if you increase the residence time, probably you will end up with degrading the vinyl chloride monomer. So this is what the theory states. These are the experimental results. So we are going to take this information, and then we are going to add it in the Aspen HYSYS, and let's see whether we get 60% conversion, or how the product stream looks like. Yeah, so let's give a try. And then so 773 Kelvin, that's roughly 500 degrees centigrade. So let's go back to Aspen HYSYS window. Let's do this. So we are going to add a pyrolysis chamber. So I'm going to use a plug flow reactor. So this, we will pyrolyze this type like in a tubular reactor. So let's do it this way. So double okay, one more thing we need to do. So we need to increase the temperature to 500 degrees centigrade and the pressure to 20 kilopascals. So let's add a small unit operation. So let's add a heater. So let's add a heater. So the heater inlet should be pure ethylene dichloride, and then let's call the outlet stream to 15. I don't know whether I used this number already. 14, no, 15. 15 is good. So just connect it. Requires an energy stream. Okay, let's put QE9. I think we already used it. QE10. For some reason it's not accepting. Let's change the temperature to I don't know why I couldn't add an energy stream here. Okay, let's put QV1. Okay, let's close this, and then in the product stream we have to maintain a temperature of say 500 degrees centigrade, and then let's close this, and then let's put go to parameter. Let's put delta P equal to 0. So which means the pressure that goes in and pressure that comes out, that should be same. And now let's increase the pressure to the to 20 atmosphere. So let's add a pump. Oh, sorry, compressor, sorry. So inlet stream should be 15, outlet should be 16, and then let's put the QV2. Unknown duty, okay. So now click 16 and then put the, okay, we have the, click on the pump and then go to parameters, or sorry, go to 16 and then click the value. We need the pressure to 20 atmosphere. So that's the condition at which we are going to perform the thermal cracking. So everything is fine. Okay, so it automatically changes the temperature. Okay, probably we should have added the compressor first and then the pump after. Sorry, compressor first and then the heater after. So I'm going to add a, okay, 613 degree centigrade. I'm going to add a cooler, why not? So anyway, we are learning, yeah? We are not doing something like a real design. We're just learning how to use Aspen HYSYS and how to make sense out of that. So let's put inlet to 16, outlet to 17. Let's put the QV3. That's our energy stream, unknown delta P. We know that. So delta P equal to 0. And then you can close this, and then we can put the temperature 17 to 500 degrees centigrade. I think everything is fine. So the pressure is at 20 atmosphere, temperature is at 500 degree centigrade. Close this. So let's connect our pyrolysis chamber. So inlet should be stream 17. Outlet should be stream 18. So you will understand everything only if you are listening to my lecture, starting from lecture 1 to now. I explained everything, the whole process to you, and then I'm just, whatever the process that I explained, I'm just making the flow sheet out of that. So this is fine. And then go to parameters, reactions. We need to add a reaction set. So you have to select set 1, and in set 1 go to details. In set 1 reaction 3, that's the pyrolysis. So you start from ethylene dichloride, and then you get two products, vinyl chloride and hydrochloric acid. So that's the, so -2, that's the reactant, and the remaining 2 are the products, and that's the stoichiometric ratio. I think everything looks fine, and it says unknown dimensions, and we know that because we didn't even mention anything about the volume of the reactor and so on. So go to overall. I think it should be under worksheet, or I don't remember exactly. So dynamics. Connections, user variables, nodes. I forgot really. There should be a way to mention now. We already mentioned the volume and everything when you were for the oxychlorination reaction, if you remember. Okay, it's in the rating here. So let's assume the total volume is say 2000 meter cube, and then I think in the literature the length to the length should be 250 meters. So, and then the volume, we just assumed a value of 2000 cubic meters. So this is fine. And then go to design back again, connection, parameter. Let's assume delta P is equal to 0. So which means the stream that enters here and the stream that enters out, the pressure of stream 17 and the pressure in stream 18 are same. So that's fine. Unknown delta P, I think it converged automatically at the moment. So where this length 250 comes from, so that comes from the from this work, so from the same paper, Lakshman et al, and I'm also following the other book, chemical process design by Demian and Bildia. I don't know how to pronounce their name. So they also use the length, the pyrolysis chamber length as 250 meters. So that's the value I used. Obviously we can change it. We don't have to stick to these things. 250 meters is a very long tube. So this is fine. And now what we have to do is, so let's go back to that PowerPoint. So let's fix the, you see the residence time to 0.35 seconds. So in order to achieve 60% conversion. Yeah? So if we increase the residence time, then we have to face the product degradation. I'm not sure whether that's the case. Let's check that. using Aspen HYSYS. So again we have to create a spreadsheet like what we did before. So let's create a spreadsheet in order to optimize the residence time. So go to the spreadsheet, let's call it so residence time of PFR. I'm just giving some title, and then let's say flow rate, and then let's say volume, and then residence time. So for the flow rate, we know it's in the stream 17. Add import variables, select stream 17, and then select actual volume flow, and then press done. So 1718 cubic meters per hour. And volume, right click, add import variable. So this is PFR 101. So you have to select that particular unit. And then select the volume of the reactor volume, add it. I think this should be okay. Oops, I don't know what happened. PFR 101, reactor volume, then press done. Yes, it's 2000 cubic meter, and now we have to optimize the residence time. So first we have to calculate the residence time. So that should be that should be equal to volume divided by flow rate, B3 by B2. So 1.164 1.164, this is in hours, okay. So we have to calculate it into seconds. So let's close this. So we did already, and then if we go back to our PowerPoint, where is that? So we need to fix the time to 0.35 seconds. So how much in hours? So let's put so we know 1 minute is 1 hour. So 1 hour is equal to 3600 seconds. So 0.35 seconds. So the residence time is 0.35 seconds. So that should be equal to 0.00009 hours. So something like that. So let's go back to our Aspen HYSYS. So let's add the adjust tool. So what you're going to do is we're going to adjust the residence time of the plug flow in the pyrolysis chamber, and the residence time of the reactants will be around 0.00009 hours. So let's try that, whether that works or not. To me it looks like a very small value. So let's add the adjust tool, add the adjust, and then select variable. So we have to change the volume. So let's change the volume, say like PFR 101, and then select the reactor volume somewhere here, select, and then the target variable, we should go to spreadsheet 2, and then B4, select, and then we are going to fix the target value to 0.1234, and then 9, and then press start. So it's doing some calculations. Let's wait for some time. It will take some time, so let's see what happens. Yes, 10 more iterations. Okay. This value is very low, and I really recommend you to watch all the videos, yeah, from lecture 1 to all, and 1, 2, 3, all the parts which I recorded. So it's time consuming, but anyway, you have to learn Aspen HYSYS, and the best way to learn is to be patient and listen to these very long lectures. Try to practice in home. Come to university, go to the lab. Sorry, you cannot practice this in the home because you don't have license to the software. So you must come to the lab, and I really recommend you to come on a weekend. Yeah, so you will have a lot of time. You can sit the full day and then develop the full process flow sheet. So you watch it in the home, take a notes, use pen and paper, and then you come to the lab, and then maybe come on a Saturday or a Sunday, and then try to perform try to develop the full process flow sheet. So that's the easiest way to learn, and try to do this for at least 2 to 3 times, and then you can also work in groups. You can talk to your friends, they may help you, and in case if they know how to fix a problem. So that's the best way to learn the software. So okay, I think this is converged. I'm going to close it, and let's click on material stream 7, right click, show table. Now you all know how to do these things, like how to add some properties, like double click on the table, add a variable. Let's add a mole fraction of ethylene dichloride. It's 99%. Close this, and then let's do the same for stream 9. Show table. Double click, add variable. Again, same. Check the mole fraction. Let's add ethylene dichloride, and also the products, vinyl chloride monomer and hydrochloric acid. I think this is good. Okay, one thing you can see now is there is almost a zero conversion. So whatever that goes into the reactor, that comes outside. So practically this residence time is not doing anything inside the reactor. So what I'm going to do is I'm going to increase the residence time to some. I'm going to increase to 0.3, maybe 0.1 hour, and then let's see what happens. Okay, it's not allowing me. 0.1. I think it's solving. I think yes, I see something in the bottom. So I think you are also learning how to play with the software, and obviously in your final year design project you may have some similar problems, and this is how you have to deal with this. So you take the value from literature, and if it doesn't work, obviously you can do something else. Okay, now I see a bit. So I see the mass component is slightly increased. You see slightly product on the other side. So I'm going to try with increase the temperature and the pressure of the stream 17. So let's click stream 17. Okay, stream 17. Let's increase the temperature to 550. And still we are waiting for the calculations for the pyrolysis unit. The results will appear soon in this table. Okay, it's slightly improved. I'm going to increase the pressure to 25 or 26 bar. So close this, so we can change that stream temperature pressure to 26 atmosphere. So you are really learning a lot. Yeah. So now we are changing the process condition and we know the reaction kinetics already. So based on according to the particular rate expression, and we are trying to manipulate the process conditions and see how it affects the conversion in the pyrolysis chamber. So we are really doing a lot of things now, and we are also learning a lot of things now. Always let's target for a 60% conversion, yeah, roughly. Okay, it doesn't improve a lot, honestly. It's around a 15%. Let's improve the selectivity. Probably let's increase the time. Let's increase the time to say 0.5. So let's try until the component fraction with respect to ethylene dichloride reaches 0.3. So these things you may not find it in the books, yeah. So we are just learning, and we are trying to learn by doing something, yeah, in the software, and checking what it can do. We are trying now, like changing the the residence time, changing the reaction temperature, pressure, and then, but we didn't change the rate kinetic expression, yeah. So, and now we are okay. This is not bad. So I'm going to increase the pressure slightly to 30 bar. I'm not sure whether that's going to make any big difference. So temperature is 550. So let's change the pressure to 30 bars. Okay. I think this should be fine. Or one thing we have to check, what's the exit temperature of the reactor. That's something we have to pay attention, and I didn't realize that. I forgot to check. Let's check the temperature. Okay, the temperature is 411 degrees centigrade, and it should be 550. Yeah, so we can do something. We call it as a set. So we have to set the inlet temperature and the exit temperature should be same. So we can do that by adding a function. It's called set. So if you see this here, Cn bracket A, so click that one. So just to check where my cursor is moving in the screen. So that's the set icon. So select that and then place it somewhere here. And what I'm going to set is the temperature in the stream 17 and 18 should be same. So double click on the set, select variable, click on the value set temperature, select, and then the source variable. This should be the same temperature. So select stream 18. Okay. Consistency error has occurred. Okay, let's press not solved. Close this and then press the active button. It will perform the simulations. Okay, still it's not converging. So what I'm going to do is I'm going to delete the set operation. run it. And then press the active button again, and then what we can do is double click on the PFR unit, add a energy stream, say QE5, QB5. Let's put unknown duty, okay. Close this, and then select the stream 18, and then fix the temperature to 550. Yeah, that should be fine now. Yeah, now the temperature, everything looks same. Yeah, 550, and then 30 kilopascal, 30 kilopascal, and then the vinyl chloride monomer. You see the conversion is better now. We almost consumed all the ethylene dichloride. So maybe now we can change it one more time, the residence time back to some low value. Let's put 0.1 and see what happens. No, okay, let's put 0.2. Okay, I think conversion is still good. Let's put 0.3. So we are adjusting the residence time in the pyrolysis chamber in order to improve the conversion. Yeah, so it's I think this is excellent. I think it's for we have equal moles of vinyl chloride and hydrochloric acid. We can improve slightly a bit, 0.6, and see what happens. At the moment, we are assuming that increasing this residence time will not play any role on the how do you call it, like on the product quality, like degradation of vinyl chloride monomer and so on. So let's put it back to 0.5. So before we all had almost a similar conversion here, 0.5. Yeah, 0.4629. So you see here almost no fractions of your ethylene dichloride. So let's close this one. Let's close this. So, and if you look at here, the product stream clearly contains ethylene dichloride, vinyl chloride monomer and hydrochloric acid. So, and our objective is to produce 100% pure ethylene dichloride. Yeah. So 100% pure vinyl chloride monomer. So we have to purify the things. Okay, maybe one thing I can do, I will make it slightly. I will make the conversion less. So in the product stream, you will have good amount of ethylene dichloride, vinyl chloride monomer, and hydrochloric acid. And then we will use a distillation column to separate these fractions. So we will get only vinyl chloride monomer, and then we will separate these two quantities, like the ethylene dichloride and the hydrochloric acid. Okay, so let's do that. So I will change the residence time to, say, let's put, in fact, that's the main, if you look at in the literature, they say they work for 60% conversion, and that's because if they target for 100% conversion, then you have to wait more time and it's going to degrade your product. So let's stick to some low value. Let's put 0.1. Let's put 0.1 and see. That's the residence time, and whatever the, irrespective of the percentage conversion or the molar concentration of the vinyl chloride monomer that we are going to see in this table 18, we will proceed with that value, and then we will try to purify it. I'm not sure what is happening at the moment. Something is not correct. Okay, let's stick to this value, and then let's try to separate a vinyl chloride monomer from hydrochloric acid and then the ethylene dichloride. So I'm going to stop the recording now. I'm going to take a break. Probably I will record, I don't know, today evening or tomorrow, and then I will show you how to design a distillation column. So that is something that you should know as a chemical engineer, and there are few tricks that we, or maybe you can say like a shortcut methods that we can perform using Aspen HYSYS. So that one it will take a bit of time. Yeah, so I will show you. We decided like to separate these three components using a distillation unit operation, but we can give some justification, okay, why we should go for distillation instead of other separation techniques. So for that we have to look into the fluid properties. So I will show you in the next lecture like how to check the fluid properties of the different components. Here in this case vinyl chloride monomer, hydrochloric acid, and then ethylene dichloride, and then from the fluid properties we can get some idea like okay, whether distillation is a good unit operation in order to, or a good separation technique to separate these components, and also at what temperature I should maintain, or what temperature I should maintain in the reboiler, or what temperature I should maintain in the condenser, and so on. So these are some, and also the number of stages where my and what's the where my like number of stages, and also condenser temperature, and another thing is reboiler temperature, and also where your feed entered, that also matters. So these things we can we should have this information before we are going to integrate the distillation column to this process flow sheet. But where to get this information? So nobody is going to tell us. So there are some shortcut methods to that allows to get such information using Aspen HYSYS. So that's what we are going to do it in the next lecture. Yeah. So next lecture is also very important, and 100% sure, like in the, especially in the final design project, you may use you may design a distillation column. Yeah, so that time you will really appreciate what you learned in this particular module. Yeah, so I'll stop recording now. So as I said, in the next lecture we are going to deal with the distillation, and we are going to deal with the distillation in a very very detailed way. Yeah, so we're going to not only just like drag and drop a distillation unit and finish the problem. No, we are really going to make a we're going to learn something, we call it as a shortcut distillation method, and then we are going to integrate something, we call it as a rigorous distillation column. So the next lecture is very important, and in the next lecture probably once I will finish developing this full process flow sheet, and then we will try to recycle the streams. So we already purified something, we separate something from something. So instead of wasting all those recovered streams, so we will recycle recycle those streams back into the process. Yeah, so I will show you also how to do that in the next lecture. So probably next lecture will be the last one with respect to manufacturing of a vinyl chloride monomer, and after that, as I said in the lecture 2, I will show you how to add some complex reaction kinetics in Aspen HYSYS. Yeah, so thanks for listening. And one thing I want to say is, like, I'm not recording these videos like starting from I don't know, from the raw material to the stream 18 which you are seeing right now at the in the screen. So I took a lot of break, and because and then whenever I encounter some problem, I stop recording the video, and then I try to figure it out what happened, why the error comes, and so on. For that I've spent few minutes every time whenever I have some issues, and then once I solved it, I resume the recording, and then finally I compile them into one single video. Yeah, so So why I'm saying this is it's like so I'm not an expert either in Aspen HYSYS. So I'm also like you. I'm also like learning the Aspen HYSYS by using the software. So the more I'm going to use, the more I will get more and more familiarized. Yeah, sorry for my pronunciation. Yeah, so the so and you must know that like if you are going to solve this problem by yourself, obviously you can do that. Yeah, so you can take notes, write every details in your notebook, go to the lab, and then you can try to develop the process flow sheet by yourself, which is really a good idea. And obviously you are going to encounter some problems. Yeah? Oh, something is missing, something is not converging. So immediately take a notebook and then write it in the notebook. Okay, when I was working with like a Reboiled Absorber, for example, it asked for a overhead flow rate. Okay, and then and how I tackled this problem. So I put some number which is less than the feed flow rate, and then I checked the purity and so on. So once I think my purity reached 99.5%, I'm happy with that number, and then I proceed to the next step. So take this type of details in your notebook. So it's really useful. Yeah, like even if you will definitely forget what you did after maybe a few months. So it's better to keep keep like especially the problems you solved, keep a record. How did you solve? And then put a title clearly, like, okay, this is some problem that I encountered when I was designing Reboiled Absorber. This is some problem which I encountered when I was designing a distillation column, and so on. Yeah, and these are the something which I realized when I was using a continuous stirred tank reactor. I took some rate expression from the literature, and then I added a CSTR tank, and suddenly I saw there is no product, which means zero conversion. So I deleted the CSTR, and then I went for a conversion reactor, and so on. So these are the things you have to take a note in your notebook. Yeah? Obviously, there are so many loads of videos in YouTube, but if you listen to those YouTube videos, one thing they will show is like they will, I don't know how they solve it like, okay, like they are like father of Aspen HYSYS, like they start and then they end without any error. Yeah? That never happens, believe me, in real life. We are going to face loads and loads of problem, loads and loads of error message, and we have to tackle it, and that's what we did. That's why I am going to edit the videos which I'm recording at the moment, but I'm not going to edit the problems that I faced while developing the process flow sheet, because you have to know, like, this could be the problem that we may encounter when you are going to add some particular unit operation in the process flow sheet. So I think these things you should always keep it in your mind. So don't take this like a advice. Yeah? This is like a part of learning process. So getting familiarized with the software, using the software, and also you have to become expert of the software, and you can become an expert only by doing it, and only by fixing the problems, only by understanding the problem even before fixing the problem. Yeah. So